bit about the purpose of visualization. So my background is scientific visualization, and in recent years, with the progress that we have made in the field of AI, I find myself more and more exploring how these fields could work together. So, and originally visualization came into being because people realized there are large amounts of data and they are really generated everywhere. Now, what is large amount of data really varies depending on which time period you look at. A plain and simple definition of large data could be data that is larger than what fits into the memory of your computer, because this is the first hurdle where you have to think about different algorithms, where you have to start paging data in from disk and stream data on demand. But this is not the end. So today we are facing data collections that you have trouble even storing on your hard drive. And for some data sets, you need multiple hard drives in a RAID to store all this data. So in the scientific visualization community, one source of big data are medical scanners. So what we see here is a CAT scanner where a patient is moved through the scanner on a bed, and while the patient is moved through, this ring rotates, and in one end you emit X-ray, and at the other end you sense the X-ray, and the X-ray is dampened by the human tissue, and by the amount of dampening that goes on, you essentially measure a absorption integral. And then you can use some reverse transforms on that to reconstruct a 3D volume where you have a regular grid of sample values, and each sample value consists of a absorption value and or density value. And now you can imagine this as a stack of X-ray images. And the question is, how do we go from this data to this colorful picture here? And the answer is we assign each density value a red, green, and blue, and the alpha value, which is how we define colors. And then we use visualization algorithms to form this picture. Another source of massive data is weather and climate simulations. And here we have the scenario that we simulate temperature, pressure, humidity, wind speed for the entire Earth, for the entire atmosphere. And this typically happens at a 10 kilometer by 10 kilometer space. So you can imagine the Earth's surface is fairly large and the atmosphere has a certain thickness. So we get a lot of data out of that. And on top of that, if we want to predict something or forecast something, then we have a start date and a prediction length, making this higher dimensional even. And if we know that there is absolutely no chance that we got the initial start values correctly, then we do multiple simulations and we vary the input guess of temperature, of humidity, depending on some considerations on the sensor accuracies that we have. And then this multiplies our data further. In automotive engineering, we are nowadays have reached a point where cars are normally designed completely at a computer, including crash simulations, including virtual wind tunnels, and also engines are designed in the same fashion. And here you see an engine, and you simulate first you simulate how the petrol burns in this engine. Then you look at a color-coded visualization of that, and you try to see if the flow is right, if there is no fuel left unburned, or if there is too many soot particles that don't leave the engine. All these are bad effects. And so then you optimize for that. And of course, this comes at massive cost savings, because you can imagine that if you have to first build the engine every time you want to test something like this, then run it for a few thousand kilometers, then take it apart again, this will be a very slow process. So, and in this case, computational simulation and visualization help accelerate the process. On top of that, a sheer endless source of data are social networks, emails, blogs, wikis, and this data is very, very unstructured. So most of this data comes in the form of a graph that grows and changes over time. And this is among the most challenging data because it's mostly natural language or videos on pictures linked to each other, and really, really massive amounts of data. So what does it mean when we say to visualize? There is two kinds of definition for visualization, and normally we say one is external visualization, one is internal visualization, and generally we mean to form a mental vision, image, or picture of something not visible or present to sight, or of an abstraction, and this is a internal visualization. This happens between you reading something and you then imagining what that could look like. So this is the internal visualization. The external visualization is to make visible to the mind or imagination by particular the use of drawings or pictures. So there we take something that is abstract or not easily seen, and we turn it into a picture, and then we show this to people. And this is what we understand as the field of visualization. So it's using the computer for this purpose. So, and normally we understand as in visualization the use of computer-supported interactive visual representations of data to amplify cognition. So what that means is we want to understand what's in the data. We want to help the user with this task. And in this talk, I'm more or less focusing on the InfoVis part. We saw medical data, we saw the simulation data. This is what we call more the scientific visualization. This I blend out a little bit because the information visualization deals with abstract data, and that is more relevant to topics that are closely related to modern AI. One challenge that we have is dealing with large numbers. And I will go through step by step through this little experiment here and try to show you how visualization can help you imagine what large numbers mean. So $1 million, the old $100 bills that you see here, they were stacking $10,000 into one bundle, and this one bundle you can squeeze down pretty much to a centimeter. So $1 million is 1 meter tall of money if you stack it up. And of course, it's a lot of money, 92 years of work for the average human on Earth. And $100 million then is 100 times that. So you have a nice pallet full of cash. 1 year of work for 3,500 average Americans, or approximately 500 homes. So now you can buy some substantial number of nice homes with that money. And then if you go up to the next one, then $1 billion essentially buys you a city. So with these numbers in mind, this here is the so-called billion-dollar-ogram that David McCandless came up with in 2009. And each block corresponds to $1 billion. So each block is worth about a small or medium-sized American city. And now we can see some things that we might find interesting. So for instance, we can see here that the OPEC revenue in 2009 was $780 billion, but the climate change fund of OPEC was essentially $3 billion. This I find personally very interesting. 308 billion US dollars were donated to charity by Americans in 2008. However, only $120 billion in foreign aid payments were given by the top 17 industrialized nations. So it seems that individuals are much more generous with their cash when it comes to charity or to help than governments. 60 billion US dollar was what the Iraq war was predicted to cost in 2003, but Iraq and Afghanistan ended up costing 3 trillion, so 3,000 billion US dollar. And of course, this raises the question if some of the money shouldn't rather have been directed towards waiving the African debt. So now a little quiz. So what were the estimated worldwide costs of the financial crisis? And each of you just think about it for 1 second and try to come up with the correct guess. Was it approximately the same as the African debt, $227 billion? Was it as much as the Iraq and Afghanistan wars? Was it all of it, 6 trillion, or even much more? So what do you think? And what really is the answer here is much more. The estimate ranges from 12 to 13 trillion US dollars, so 11,900 according to McCandless was the total cost of the crisis. And again, this is a one with a lot of zeros, so we can't imagine that. But $1 trillion is essentially this much money on pallets. And 12 trillion, you can essentially stack them into high-rise buildings around the Statue of Liberty. So it's an unimaginably large number of money. So and if you go and you check online how many US dollars are in circulation, you will see that the number of US dollars in circulation might not even be enough for this loss. And the question is, how can we burn through more US dollars than are in circulation? And the answer is that most of the money that was burned here was bookkeeping money. So considering the stock markets, considering the cash flow now, we have much, much more electronic money than we have printed money. Let's have a look at another example, how visualization helps. So now we understand that visualization can be very helpful to imagine really large numbers and large dynamic ranges. This here is a timeline of a global media pandemic and between 2000 and 2010. And you see here people somehow worry every now and then about killer Wi-Fi, that Wi-Fi is causing cancer. Killer wasps and mobile phones and cancer. Well, in 2007, when the mobile phones kicked off, that was a concern. Then came back in 2010. It has become a little bit more quiet because we survived mobile phones at a large. And then here we have violent video games, the bird flu in yellow, the swine flu here, which was an incident in 2009, one pandemic, and SARS was another pandemic, and the bird flu. And so we see that if we plot this over the timeline, then we can capture something interesting. So yeah, oh yeah, here's still the Millennium Bug hiding. If you remember that, if not, what that was is essentially programmers going cheap on memory and just encoding the 2 last digits of a year into 7 bits to save some space. And now everybody was concerned that in the year 2000, it would create a overflow and would reset to 00. And the fact that it didn't happen is mainly to be attributed to the fact that large tech companies massively spent money to fix it before the year 2000. Asteroid collisions, always a concern. Killer wasps, you see here that they align with the summer. So there seems to be some period, summer to fall. The violent video games here, we start to see patterns, and this is another thing why we use visualization, because we are very good at recognizing patterns. So what happened is November, the Christmas video games come out, and April 99 was the Columbine high school shooting that kicked off a discussion about video games, because the murderer that killed his schoolmates was known to play shooter games. And this here is a striking lack, and honestly, we don't know why. Maybe there was something more important happening at that time. Anyway, so how many people actually died? So SARS, killer wasps, bird flu, swine flu, they are actually pretty bad. Killer wasps mainly because they cause an allergic shock, and they're quite dangerous then. And if we compare this, if we try to correlate this with the with the perceived severity, so there's not much media buzz for killer wasps, but it's actually a real problem. And at the same time, we have swine flu roughly corresponding to the impact, and SARS not quite, and bird flu also not quite. So these are things that you can find very quickly with visualization, both trends and outliers. Another example here, military budget. So it seems the USA is spending a lot of money for the military, but we know that in 2008, other countries were also pretty good. So the GDP in 2008, so this is 12-year-old data, by now China has caught up with the US GDP. China is a very, very close second, but back then they were about 1/4. So if you relate these numbers, then the US has the combined GDP at that time of 4 large nations. And if you combine their military spending here, then you see that it's not even close to the US. But if you express the military budget as percent of the GDP, then suddenly Myanmar takes the lead, 26%, 1/4 of all the money that is produced as the GDP in Myanmar goes into the military, whereas the USA only has 4%, which is probably much more sane. Another thing in terms of absolute visualization against relative visualization is who has the most soldiers then? The answer absolute is China, 2.1 million, but we know that North Korea is pretty, let's say, enthusiastic about their military. So let's have a look at that in relative numbers. So as number of soldiers per 100,000 people, Korea has 4,711 North Korea. So this is 4.7% of the population serves as soldier. And now why this matters is that many things that we see and that we realize as humans are happening on a relative basis, not on an absolute basis. So that brings us to the question, after having seen some examples, why is visualization good? And as we say, a picture is worth 1,000 words. But Ben Schneiderman, one of the most influential people in visualization, he says the purpose of visualization is insight and not pictures. So it doesn't matter if you have a pretty picture, if it's not informative, then it's not a good visualization. And the reason why we bother with pictures at all is because vision is the dominant sense for acquiring information in our world. And almost 1/3 of our brain is devoted to processing of visual information. And in contrast, only 8% for touch and 3% for hearing. And these are fairly important senses as well. So now this ties back to big data as well. Hal Varian, Google's chief economist, in 2009 said, the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, That's going to be a hugely important skill in the next decades, because now we really do have essentially free and ubiquitous data. And of course, this was 2009. Nowadays, we have even more data because we are collecting this data, among others, to train our new AIs. And what is really important here is to understand, to process, to extract value. So you may have heard this, that saying that data is the new oil, but you have to refine it in order to make money from it. So that's a real difference between oil and data. So you can sell crude oil, but raw data is hard work before you get to the value. And visualization helps with that. So and there are three phases of visualization. Visual exploration, where you know nothing about the data. So you want to find unknown, unexpected things. You want to see features, structures, generate new hypotheses. Then we have the next stage where we have some hypothesis, and this is the conformative visualization, where we want to know, are we right with our assumptions, and where we drill down to get to the information. And then we have the presentation, where we just communicate our findings with other people. Let's have a brief look at the history with that in mind. So you might think this is all high-tech and very new, but it's not true. Visualization dates back thousands of years, and one of the oldest examples is this map here from Turkey, 8,200 years ago. Somebody came up with the idea of imagining what it would be to look at the city from the top, a bird's eye perspective. At that time, people were not able to gain this perspective. This is an imaginative process where people say, okay, if I go forward, I read this as up on my map, and if I go back, I read this as down on the map, and then left and right correspond to left and right. So we have one axis flip, and on top of that, the imagination and the abstraction of the actual city into something that is effective, that gives you information that you cannot gain by looking at the real city in the first place. Because if you're standing in front of the house, that's it. You don't see what's behind the house. Very important step. So maps then became more and more popular in various levels of abstraction. So here we have a map on clay from Iraq, 4,500 years old. And you see here, this is a map mostly probably intended for travel or for logistics, because it says, okay, here are mountains. So that might be a valley. So you can't really enter the valley from here or from there. And then we have a river. This is good for ships. And then we may have some routes or roads that go to this town. And also interesting is here the indication of east and west. So then later in the 10th century, in Europe, the astronomers usually assumed that the Earth is the center of our solar system, and that creates all sorts of troubles. So if you track over time the inclination, that is where you see under which angle you see the different planets and the sun, then you will see all these wobbles. And these wobbles are the result of the fact that Kepler's law wasn't known yet, that we essentially have this ellipsis and everything moves around the sun. But again, this is an early example for a time series, for a one-dimensional function. Then we have the map of Jon Snow, which is a different guy from this one. It looks like this. And this Jon Snow in 1854 was looking at the cholera outbreak in Soho, London. And he used visualization to gain his insight. So he essentially took a map of London, and then he used bars to indicate how many cholera cases he had. And then he saw something interesting. He saw these pumps here, and near this pump, there were many more cases than over here. So the people that contracted the cholera were taking their water from this pump. And this was groundbreaking because until then, people assumed that the cholera is transmitted airborne and not by water. And so in this case here, visualization is truly used to gain new insights. This here is another famous example. This is the loss of French army soldiers during Napoleon's Russia campaign. So the people moved in, the French, and then the winter set in when they reached Moscow. And you see here the temperature dropped sharply. And when they had to cross rivers, they lost a large deal of their army because the thickness corresponds to how many people made it out. So 422,000 soldiers went on this Russia campaign, and only 10,000 came back. And you can relate this here as kind of a time graph with the temperature and with the geographic location. So this is one example where troops reduced almost by half when crossing this river here. Train schedule between Paris and London. So the way to read that, this here are the hours, and whenever a train moves, he only moves forward the train. So that means that the lines have this direction. Right, so this here is coming into Paris, and this is leaving out of Paris. And you see here where you have these breaks. This is where the train rests, where the train waits. And you can see, okay, in Dijon, which is a larger city, you have some layover, and then you travel on, and you see here that between Lyon, leaving 7 in the morning, you would be in Paris at around 6 p.m. And this is the modern express train, which takes 3 hours. So the angle here tells you how fast something is. So now we as a community have tried to formalize the process of visualization, and we have this very simple model for visualization where we have data that goes into a visualization pipeline, and then you give an image to the end user, and hopefully the end user uses perception and cognition. So he looks at the image and tries to understand what's in the image to gain knowledge. And then he plays around with the parameters, looks at the data from different angles, and then he goes back to the visualization expert, that's us, and modifies the specification. So then he comes back and says, I think I saw something, but I need you to implement this and that feature for me. And this is an iterative process. So there's 2 different groups in the loop. One is the domain experts. They are the people with the data, with the simulation. And then the visualization experts who kind of are interdisciplinary and try to speak the same language to bridge this gap of different fields, and then try to come up with clever ways to visualize things, to generate pictures such that the domain experts have a streamlined workflow. Let's have a look at a few definitions. So computer-based visualization systems provide visual representations of data sets designed to help people carry out tasks more efficiently, as I mentioned before. So this book here is fairly famous by Tamara Manzner, Visualization, Analysis, and Design. So this is what she has to say. And if you think about it, it makes sense to have a human in the loop, because if you have a fully automatic solution, like an AI, that you can trust, that you understand, then you don't really need that anymore, because then you can answer questions by compact and precise queries. And if this decision can be automated, then you don't need the visualization. But these cases are usually rare, and we are just beginning to understand how AI can automate some of these processes and others not. Here's an interesting example. Why don't we use statistics? If we have too much data, just let's have some aggregates and look at statistical indicators. So, and this here is called Anscombe's quartet. These are 4 data sets, and they all have identical statistics. Same mean, same variance, same correlation, same regression line. Okay, so they should be the same, right? Let's have a look at them when we plot them. The first one is nice and scattered around the regression line, so this is a good data set to do statistics on. The next one has a nonlinear trend, and therefore the regression line doesn't give you much information. And the last two have outliers. And with outliers, again, the statistics don't give you a good indication. But moreover, all of them have the same. Looking at the visualization, there is no way you detect this. And then another group took this up a notch. They introduced the data source dozen. The data source dozen looks like this. All of these distributions have the same mean, the same standard deviation, the same correlation, but they're vastly different. I mean, one is a star, one is a dinosaur. So, and the problem here is that statistics aren't enough to describe the look of data. So talking about the look, this is sometimes called scagnostics, measures to describe the appearance of scatter plots. Same example of the data source dozen with different visualizations. You see that the box plot here indicating the standard deviation, the mean, the min, the max doesn't change. These density plots do, and therefore arguably this box plot here is not a very good idea for this data set. So then what is wrong with statistics? We have made the wrong assumption. If we assume that we have normal distributed data, then we can do all the statistics. Then mean and standard deviation are meaningful. But often we don't have that data. Like here, this is not data that scatters around a regression line. So we have a very poor fit for the regression line. Essentially, any line you draw through the data is about as bad as the other. And the other pitfall that we have, if we don't have enough data, if we don't, then this this also doesn't work. Sorry, just give me 1 second. Okay, so here the assumption is that with 2 numbers, yesterday no husband, today 1 husband, you assume, okay, linear line fit, so you will have a lot of husbands in the future. And then she says, well, you should have more data. And then he says, okay, let's put 0 husbands, 0 husbands, 0 husbands, 0 husbands. And then it's even worse. And the reason is that extrapolation is never to be trusted. So you need enough data to cover your domain in order to make a decision. And outside of the domain that is covered by your data, you hope that it works, but there's no reason to assume that. So statistics only work for well-specified problems, and many analysis problems are ill-defined, and you don't typically know exactly what the question is to ask in advance. And therefore, you try to detect and discover the unexpected. And this is very important because visualization tries to augment human capabilities rather than to replace people with computational decision-making methods. So visualization is strongest when you try to understand what your actual problem is. Why do we have a computer? Well, try doing this by hand and then realizing halfway through that one of the circles, the data has changed over time and you should draw it a little bigger. Same here, so it's just too tedious and completely infeasible to do it by hand. So, and the computer can do it fast, so you can manipulate the data and use interactivity. So why is this interactivity a good idea? Let's have a look at this here. This is, of course, a search task. And what makes the search task hard is that, first of all, there's a lot of structure in this image, a lot of features. And the other one is there's only a very small data element that you're looking for. And how can visualization help with that? Well, currently you're probably going through the picture like this. Try to find where's Waldo, where's Waldo. If you use color, you go into what's called pre-attentive processing. Without spending any cognitive effort, Waldo pops out and you process the entire image at once. Before you were in sequential processing. And these cognitive considerations are very important to design effective visualization. So here's a spot the differences. And same thing, you're probably scanning, but now you're also creating a mental map. So you try to memorize where you saw something that may be different in the lower frame, on the top frame, so you're memorizing. And this is made very hard by the fact that they are separated. If I put them on top of each other and I go back and forth, you immediately see the changes. So very, very simple. So interactivity is good because it allows you to guide the user's attention. It allows you to open another toolbox of tricks to guide the user to the important features in the data. So, and interactivity essentially handles data complexity. So it's infeasible to look at the whole data. So normally you first give an overview first, and then you let the user select the data one aspect at a time. And this is what Ben Schneiderman calls overview first, zoom and filter, then details on demand. This is how you understand data. So why do we use vision? Well, I mentioned it's the highest bandwidth channel to the brain. And sometimes you immediately detect interesting visual structures and relationships. And I demonstrated the sequential versus parallel processing as well. Here's another example. So the red circle immediately pops out as something important. Here's a little harder because now we use shape as the main criterion. And this here is much harder because now we mix this is much easier because now we have two visual channels, the shape and the color, to distinguish the two sets. This here is the one that is much harder because this here there's a red sphere hiding, and here we are essentially breaking our own visualization. Why should we focus on tasks and effectiveness? Well, which problem do we want to solve? Here's a London Underground map, and this is the standard underground map until it was replaced with what we know today. And this map is very good at answering, how do I go from my home to the nearest subway station? Because at that time, this was probably a bit more a hassle than today. So, and then when it was first proposed, this map here got rejected because people were too used to the other one and because it answered a different question. This here answers the question, what is the fastest path from A to B, under the assumption that I'm already at the station or know how to get to the closest station. So, and the reason that we need these specific visualizations for specific tasks is for us a good news, because it means we have a job. If there was one visualization for everything, then somebody would have discovered this by now, and then I probably would be in another research field. So, and as we saw, tools have to really match the problem. It's the same as if you try to put a screw in a piece of wood with a hammer. So you need specialized tools for the problem. And luckily, most possibilities are ineffective. That's why this is an active research field. Another thing that we normally require is that representations should be correct, accurate, and truthful. And here's an example for that. If you take a pie chart and you tilt it, then you're essentially lying with visualization, because here 19.5% seems to be larger than 21.2%. And to put that into context, this happens because you, of course, have perspective. So area shrinks further from the camera. And this was Steve Jobs making a point that between RAM, which is the BlackBerry phone, and the Apple phone, there's almost no competition, neglecting that 21.2% of the market was still using other vendors. This here's another example. So here, the trick is that you shrink the doctor to represent the percentages in both X and Y direction. And therefore, the doctor appears much too small. So this doctor here should be a little less than half the size of this guy, but it's perceived as about a quarter. So, and this is what we call the lie factor, the size of effect shown in the graphics divided by the size of the effect in the data. Same for the $1 bill. So this here should be 44% of the perceived size of this $1 bill here. And because this here is the ground truth, and then in Carter's time, 1978, the inflation had reduced the purchasing power of $1 to 44.1958 cents over 20 years. But again, since you shrink it in both dimensions, the dollar looks much, much too small. Same here with oil barrels. And this here is $13.34. And this here is, for instance, $10.46. And you can now do some math and estimate how many of these barrels you fit into the large barrel, and the proportions are all off. So you suggest something more dramatic than what is there. And this is typically done if you have an agenda behind your visualization. This here I found online is people now argue that truthful to the data means that we should use absolute numbers. And then global warming critics have figured out, well, if they understand one thing, then how to push an agenda. They have figured out that there is absolute zero for temperature, and we measure from that absolute zero in Kelvin. And of course, if we plot that, nothing will happen, because we're talking about 1 degree, 2 degree versus 290, 270 degree. So, and maybe what we should be looking at is at what we are really interested in. We should be looking at the annual mean, and we should do this as a incremental, and then we get this here. And this seems to clearly indicate at least that, well, it proves that between 1880 and 2020, the temperature has risen by about 1 degree. And the data suggests that this trend will continue if we don't do anything about it. So, and then this also means there are limitations. Computers, humans, and displays each have limitations such as processing time, number of pixels, perception, attention, and memory. And what I want to show you briefly is change blindness. So this is fascinating. So between the two images, there is some difference. And you can spend some time looking at it. And I told you, if you put them on top of each other and you flip between them, then it's very easy to find this. But now we're making one very subtle change. We are slowly fading from one image to the next image. And while we're fading, I want you to look at it and see if you detect the change. So, okay, now we're slowly fading. I hope this works. Yep, we are fading. Now just have a look at it and try to see what is the difference. And now we're at image B. And I would bet many of you didn't really notice anything, because I'm hiding the difference in a very gradual crossfade. If I flip back and forth, you will immediately see that it's a fairly large change in the image, but since since it doesn't pop out, you don't have this pop out effect, you're permanently trying to scan the image. So now I want to do something similar. So we're going to do another one side by side, and I want you to focus and find the difference. And then you just give it an effort, and then afterwards I tell you what the difference is. So here we go. So the difference is fairly subtle. It's essentially this man here is wearing different pants. But what I did here is I guided your attention to these two pictures. And now we're doing it again. But now you look at the Hamad bin Khalifa logo up there. So, and I bet most of you didn't spot the cat the first time. And this is your brain operating fully normal. So we have so much visual information in the world, you cannot all process that. And therefore, your brain filters out irrelevant information and focuses only on the relevant parts. And now if I guide your attention away, then you miss that. And that is why it's so important to guide the user's attention to the features that you extract. So here's the cat again. Okay, and there is a psychologist, Daniel Simons, who studies this, and it's fantastic. So let's have a look at a video, and you just follow the instruction of the video, and afterwards I'll talk about what happened. Okay, let me see if the video works in this scenario. Oh, okay. Sorry about that. The video is not working. I encourage you to go. Apologies for that. I encourage you to look up Daniel J. Simons and Change Blindness. You find these videos on YouTube, and especially this here is very, very interesting. So the basketball video. Try after the talk to go online and find this video. Okay. So then last, I want to talk a little bit about other uses in combination with AI. Normally we train neural networks in a supervised way where we show them images and we tell the network, look, this is a cat image, and here's another one, and here's a dog image, and here's a dog image. And then after several epochs, we show it an image and it tells us, oh, that is 97%, I'm certain this is a cat. And we show it a dog and it says, yeah, 96% dog. Now, what happens if we have outliers in the data? Believe it or not, this here is a dog. He just looks weird. And if we feed that in and say, look, there's a cat. And this cat here, we say, look, there's a dog. Then after some while, we can confuse the network. So we can show it the cat, and then it will say, not certain. I saw this as a cat, and also then again, it has some features that look like a dog. So, and the same for the dog. And the problem here is again that we have to remove these outliers for training AI. Otherwise, it doesn't generalize very well because you fed it false information. And this is an active research topic right now, very hot research topic, how to deal with incomplete, with fuzzy, with contradicting labels. So for images, it's easy. We just look at the data directly to find the outliers. But for abstract data, we need to look at a picture of the data to find the outliers. So here we would erase this data point and this data point. And so this brings us to the question, how do we find these anomalies and also the structures? So we have the explorative phase. Then hypothesis forming, is there a model for the structures? If we remove this outlier, yeah, there's a linear model and a linear model here. And then regarding the presentation afterwards, how do we communicate these findings? And how do we even start or begin to understand neural networks? And this here is an example of a Google blog where the researchers were thinking about what does a neural network look for? And of course, the lowest layers in a convolutional neural network, they find edges. Then they find more and more complex structures. And you see that these complex structures here start to resemble parts of the images in a very, very weird way. And this is called feature visualization. So this is an attempt to understand how neural networks actually work, because so far our theoretical understanding of neural networks isn't very strong and is still very incomplete. And if you attended the talk of Dr. Marco, my colleague, yesterday, then he probably talked about this histopathology project where we use AI for the purpose of visualization. So we train with these data sets here and labels. We train a classifier and a segmenter. So essentially, first we train the segmenter, then we have these cutouts of the cell nuclei. We label them, we give them and train a classifier. And then our segmenter, if we show him a new sample of tissue, finds the outlines of the cells. The outlines of the cells we give to the classifier, and then we get a final picture where we see structures. And here AI is integrated in the visualization pipeline because AI takes the data into something visual. Okay, with this, I would like to conclude. The purpose of visualization is really insight, not pretty pictures. And you touch on domain scientific questions as well as on psychological and perceptual questions. And this is why I think this field is very, very interesting. Okay, are there questions? Thanks for your attention.
Thank you very much, Doctor, for the enlightening talk. Hope our viewers have a better idea on what visualization is. So there are some questions from our viewers.
Of course.
Yeah. So the first question is from Soheb. How does visualization help the decision makers, basically?
Yeah, so in many different fields, decision makers usually have their abstract data, and then they want to spot some trends and outliers. And normally, a tool of choice to do that is you use a visualization package like Tableau. And you look at the data, and then you have analysts that try to spot if everything is correct or not. So, for instance, we have here in Qatar, hospitals are reporting to the Ministry of Public Health, and the Ministry of Public Health is using a tool called Power BI to look at the reported data and to look at the key performance indicators. And based on these key performance indicators, they can then offer recommendations to hospitals, such as your staff has to be more friendly, or you have to make sure that your employees disinfect properly. And this is being used right now. So also visualization can, of course, help decision makers at big companies in the form of financial charts. Just with one quick glance, you see if the company goes through a hiccup on a periodical base, or if this is a systemic trend.
Thank you, Doctor. Our next question is from Mohammed. So, can visualization tools manipulate data that change the instantaneous? Can that changes instantaneously and permanently? And does it embody in it in real time?
Yeah, this is a very good question, because this is at the core of what visualization wants to do. So, and it's a very tough task. It depends a lot on the data, but normally what we also look at are dashboards for fault prediction, where you have a company, and this company wants to know if their assets are working properly. And if they fail, then you would alert them. So another part of the story is where visualization actually triggers the simulation. This is called computational steering. So in that case, if you do your car simulation or your crash simulation, you can, with a slider, change the parameters of the physical simulation and then trigger a rerun of the simulation and immediately look at the results. And time-dependent data is very, very exciting, not only if it changes permanently, but any time-dependent data is very exciting because this data frequently lives in higher dimensions. Like even if you think about climate, this lives in at least 4 dimensions because you have the time on top. And then the question is, how do I map the time to screen? Do I keep the time? Do I show animations? Or do I do a timeline and then plot over the timeline? So there's still some active research in that, but some tasks such as time series plots are the easiest ones that are solved.
Yeah. So one more question from Mohammed.
Mm-hmm.
So is there a correlation between series time and ranking?
You can do that. So this is again, if you have a time series, this is just a function over time. And if you have many of them, then you can define a rank as the most representative function in these time series. And then essentially what that means is how many, like a median. So you peel off time series that sit on top and on the bottom, and the one that survives gives you the best representation of the dating of the data. But ranking generally only refers to a list 1, 2, 3, 4, 5, and time series is really a continuous measurement over time. I hope this answers the question.
Thank you. Moving on to the next question from Amin. What are the criteria on which data visualization relies in analyzing data and dealing with the big data?
Okay, so generally speaking, we have this abstraction of the workflow where data comes in. Then we have a filtering stage where we can clean up the data and select data. And then we go into the next stage where we decide how to assign visual channels like color or shape or texture to our data attributes. So, and then we turn this into a renderable representation and we can show it on a screen. And so with big data now, the challenge is to just show the data that is relevant. As a simple example, I've worked with one data set that was 32 terabytes for one time step. This is a early universe forming simulation. And at the same time, I know absolutely certain that my screen only has 8 million pixels, but I have 8 million pixels and 1 trillion particles. So, and there will be overdraw. There's absolutely no point of showing this data set in the entire detail. So what you do then is you compute a hierarchy and you try with your hierarchy to make the best use of the pixels that you have. And in that case, this is how you deal with big data. So you select data at the right scale to fill your screen. If I want an overview, then I have to have an averaging going on that kind of aggregates the data into something that I can display. And if I want to zoom in, then the detail is there. And then I cut away data left and right that doesn't fit on the screen. So this is kind of how visualization deals with it. And at the same time, one of the fundamental criteria in visualization is I still want to be truthful to the data and I want to help the expert. So if I come up with a very, very nice, very pretty visualization, but that is so different from the workflow that the experts have, then they won't use it. So in some cases, if you have more conservative fields, you have to change very, very gradually in your visualization and implement a lot of legacy features that the experts are used to. A friend of mine worked on weather forecasting meteorology data, and he always put a 2D map on the bottom and top in addition to the 3D. So, and then he projects everything down, because the experts, when he started this project, were working in 2D, and they had some benefit of the 3D, but it took them time to learn. So there was a learning curve, and they had to turn the features on and learn what it is that visualization gives them. And this transition phase you always have to keep in mind as well. This is another criterion on how to design a visualization that is used.
Thank you, Doctor. That brings us to the end of the Q&A session.
Okay,
Yeah.
thank you very much. Has
Thank
been
you,
a pleasure. And see you around. If, by the way, if you have questions later, you're welcome to post my email as well, so that people can contact me later if they see the video and have questions.
Sure, Doctor. We'll post it in the comments. Once again, thank you very much for the great talk. Have a nice day.
Thank you for the invitation. Bye.